So we have the inner radius. So we'll say r sub I equals 7.3 times 10 to the 7th, 10 to the 7th meters. And then the outer radius of the rings is going to be 1.7 times 10 to the 8th meters. We also have the mass of Saturn equaling 5.7 times 10 to the 26th kilograms. So we know that the velocity is going to be dictated by the equation, we'll say, and we know that this is also equaling 2 pi r divided by t. So we can solve for t and say t, the period, is going to be 2 pi times r cubed divided by g times m, the mass of the planet. And so we can figure it out. So t inner is going to be 2 pi times the square root of r cubed, so 7.3 times 10 to the 7th cubed, divided by 6.67 times 10 to the negative 11th times the mass of Saturn. So this will be 5.7 times 10 to the 26th. And we find that the period of the inner rings is going to be 2.0 times 10 to the 4th seconds. The period of the outer rings would be equal to 2 pi times the square root of 1.7 times 10 to the 8th. And this will be divided by 6.67 times 10 to the negative 11th times, again, 5.7 times 10 to the 26th. And this equals 7.1 times 10 to the 4th seconds. So we know that the period of Saturn itself is going to be equal to 10 hours, 39 minutes, which is approximately equal to 3.8 times 10 to the 4th seconds. So we know that the inner rings are less than Saturn. The period of the inner rings is going to be less than the period of Saturn, which means that the inner rings move faster relative to Saturn. Now, the period of the outer rings are greater than the period of Saturn, which means that it has a lower angular velocity. So this means that the outer rings are going to move slower relative to Saturn. And that's the end of the solution. Thank you for watching.